Okay, so we're doing problem number, what is this problem? So this is problem number 27, and this is Kirchhoff's laws. Okay, so problem number 27. So problem number 27, right? And I think I'm going to change markers soon. Okay, problem number 27 says that we have a battery, two batteries. So here's our batteries. And we'll label this as V1. And then we have a resistor, and then we have a resistor, and then we have another resistor, and then another battery. Oh, my diagrams suck. I guess I'm no Picasso. Okay, so this is labeled as R1, R2, and we're told, so I'm not going to use any numbers. I'm just going to say it's R1, R2, R3, R4. So this is R1, this is R2, this is R3, and this is R4. And we're told what these values are, but we're actually going to be using Kramer's rules and Kirchhoff's laws, so there's no point in doing these. Can you even see this on the board? Anyway, and I'm told that this node, the current is, currents are going away from this node, so I don't know what the labels are, so I'll put that in a sec. So we're told that I1 is going up, I2 is going to the left, so this is I1, and this is I2 and I3. So I1 is going up, I2 is this way, and I3 is going to go this way. And we're going to label this as V2. Okay, I'm not going to put any numbers in this, we're just going to do the abstractly and get the answer for I1, I2, and I3 in terms of Kramer's rule. Okay, so let's, so we need to, there are three unknowns. We don't know what I1, I2, and I3 are, so we're trying to calculate I1, I2, and I3. And so we can use this node right here. We could say the sum of all currents is equal to the sum of all currents leaving. That's Kirchhoff's current law. So sum of the currents coming in, 0. So Kirchhoff's current law, or Kirchhoff's current law, KCL, says that this is the currents coming into this node is 0. No currents coming in, but all the currents are leaving, so this is I1 plus I2 plus I3. So remember, this is just, we don't know what the direction of the current values are. Current might be coming down or up, we don't know. Might be going left or right, we don't know. But we just assume we're constructing these variables, I1, I2, and I3, saying that I1 is a variable that represents the current going up, and I2 is a variable that represents the current going to the left, and I3 is the current going to the right. And that's an assumption. That's just our construction of these variables. And so we have set these values as I1, I2. Of course, if we make a mistake, we'll get a negative answer in 1. So if I get a negative value for I2, that means that current is flowing in the opposite direction, which is most likely because the positive side of this battery is on the other side. So most likely all of my directions are going to be negative. But it doesn't really matter. The whole point is construction of Kirchhoff's laws and applying Kirchhoff's current laws and voltage laws. So KCL. And the question asks you, I'll actually write down all three loops for the voltage laws, just to make sure you understand the procedure, but I'll only use the three of the equations. Using clockwise direction for all the current loops, so clockwise, write the Kirchhoff voltage loop equations and node equations. So here's a node equation for this point, and we're clockwise is this way, hopefully. I do make mistakes, so, and this is clockwise this way. So this is loop number 1 and loop number 2, and there is a final loop, loop number 3, and I'll put that in. Actually, you know what? Since I only need to end, I have something to do after this, so let me finish this very quickly. So I'll just do loop 1 and loop 2 to get the idea. So the current is flowing this way, and because the current is flowing this way, this must be a higher potential than this. I'm going to label this plus and minus. So the current is flowing, I2 is flowing through here. I1 is flowing through here, so this must be a positive and this is a negative. So the current is going from a higher potential to negative. That's my assumption. And I3 is going this way, so this side it must be a higher potential than this side. And the battery has a plus and a minus. So let's go to the current loop. So this is Kirchhoff's voltage law, and I'm going to apply it for loop number 1. Okay, loop number 1 says I'll start from this point over here, and I'm going and going, and then it went from a higher potential to a lower potentials. So I dropped in potential V1. So you notice I went and dropped from plus to minus. I dropped. And then I went from plus to minus, so I dropped again, so I'm going to put a minus. And how much was the voltage drop? It's proportional to the current going through the resistor times R1. So this is, the current going through there is I2 times R1. Hopefully you saw that. So the sign here, right, is because I dropped in voltage from plus to minus in my traversal of that loop. I could go in the opposite direction, but the problem asked you to do it in clockwise loop. Clockwise traversal. And so now we're hitting this resistor R2. I went from minus to a plus, so that's going to be a plus, minus to plus. And then what's the current going through here? It's going to be equal to I1 times R2. Hopefully you saw that, right? And then we're back to the point A, so that's equal to 0. And the second equation, KVL2, right? I'm going to start from this node again, and I'm going to go up. I went from plus to minus, so I dropped in voltage. So this is going to be a minus, plus to minus. So how much did I drop in? It's actually the current I1 times R2. From here to here, R2. And then I went, oh, I didn't put the plus or minus on this side. So remember, I3 is going through this this direction. So this must be the positive side. This must be the negative side. Current I3 is going through this resistor. So now that I set that up, boo-boo, a little mistake. So here is going from I1 R2, and then I'm going from minus to plus. So this is so minus to plus means it increased in potential, so plus. And how much? It's going to be the current I3 times R3. That's the voltage drop across here. And then I went into the battery. I went from minus to plus, so I gained in potential, V2. And that's equal to 0. We have 3 equations. We can substitute numbers, but there's no point. We can actually do everything in calculation. So I'm also testing to make sure you understand how to use Cramer's rule and stuff, right? So that we know how to solve like linear equations. Remember, linear equations is the one thing that we can do well. Nonlinear equations we don't know very well in mathematics, but linear equations is something that we know pretty well, and we know it pretty well for a couple hundred years. Okay, so I have 3 equations, so I need to convert this into a matrix form. So the first equation is going to be, so I'm going to keep, so the unknowns are going to be here, I1, I2, and I3. And here is my arguments and my knowns, which are going to be on the left-hand side. So this is going to be 0 for the first one. So it's 1, 1, 1. Hopefully you can remember this. So that's your first equation. Second equation, I'm going to move the V1 to the other side and look at what's in front of I1. So I1 is going to be R2. R2, so this row times this column. R2 is in front of I1. And I2 is going to be minus R1. And then there is no I3, so this is going to be 0. So that's from the second equation. Okay, and the V1 is on the other side, so this is V1. It's actually, you know what, maybe I'll actually convert this. I'll do it manually just to make sure you understand this. So it's 1 times I1 plus 1 times I2 plus 1 times I3 is equal to 0. First equation. Second equation, I'll put this as I1 times R2 and then minus R1 I2, and then I'll move the V1 to the other side, so this is V1, and I'm going to repeat this process again, so this is minus R2 I1 and where's R2? So that's 0. So plus 0 times I2, and then there's a plus R3 times I3. So there's actually a 0 times I3 over here, and that's equal to minus V2. So I actually made sure that you could understand. I didn't do it in my head. Actually, I just wanted to convert that just to make sure you understand. So we've got R2 minus R1, 0, and that's equal to V1. And then there's a minus R2, and then there's a 0 here, and then there's an R3. And great, we now have a matrix equation. Whoops, I forgot this element, which is minus V2. And so we can actually calculate very quickly, right? So remember, I'm asking you to write the procedure, and my marker is dying on me, so hopefully let's try this before I use a new marker. I have to order some new markers. So let's calculate I1. What is I1? I think I can, let's put I1 over here. So I1 is the ratio of two determinants. So the bottom determinant is going to be always the same, this matrix. So it's the determinant 1, 1, 1, R2 minus R1, 0, minus R2, 0, R3. And then the top determinant is going to be, so I1 is, this is the I1 column. I'm going to replace it with 0, V1, 0, negative V2. So this is going to be 0, V1 minus V2. And the rest of the columns stay the same. So this is 1, R, 1, 0, 1, 0, R3. So when we calculate these determinants, we'll be able to get our answer. And that's the ratio. On an exam, I don't want you to actually do these calculations because they're quite cumbersome, and I'm trying to make sure you understand the concept. So I'll be giving you a problem like in determinants, but I don't want you to calculate these by hand. They're too long. It's time consuming. I will just give you an example of one determinant maybe and try to make sure that I know that you understood how to calculate determinants. Okay, so what's I2? I2 is the bottom determinant stays the same. So it's basically this matrix, right? Determinant of this matrix. And please don't forget the determinants, okay? Actually, it's kind of annoying when you see engineers, they've used determinants, and as a physicist, right, I use determinants and matrices and I mix them up, so make sure you put DET. Some engineering authors and stuff, they tend to leave it out because they're working with determinants, but as a physicist, I work in determinants and matrices, and you're going to mix them up together, and you might confuse like a multiplication times a number. A determinant is a number. This is a number. So the bottom stays the same, so it's 1, 1, 1. Actually, I'm going to look it up because my handwriting is so terrible. And this is 0, and this is minus R2, and 0, R3. So you just have to calculate this determinant once and put it always at the denominator. And the second determinant, the top determinant, is going to be, well, this is the I2 column, so I'm going to replace it with 0, V1, V2. And so it's basically same as your bottom matrix, but the second column is replaced with your other side. So this is 1, R2 minus R2, and we're going to replace with 0, V1, and minus V2, and 1, 0, R3. So at least we have a bunch of zeros and ones. So if I had to calculate this, I'd probably expand the determinant along this row because it seems to be the simplest. Even though there's 2 zeros, I like the ones easier. And the top one, actually, I like there's a 0 already, so in place I like the 1, 1. So that's probably a row that I'd like to expand on. And actually here too, so this would be a nice row to expand on. And so there's at least a 0, and there's ones. These are nice and easy to calculate. Okay, so I won't do I3 because I have some work to do, so I'll assume that, so if you have any more problems, yeah, so that's it. So this is number 27.